Alright, in the first step, you treat this alcohol in the first step of acetal and ketal formation, you treat that alcohol as a nucleophile. You protonate this, and then it attacks there, and you get an alcohol up here, and the O between the two alkyl chains down at the bottom, ether. Then in the next step, you make this alcohol into a water-leaving group, and another equivalent of the alcohol attacks. And this is considered a hemiacetal, and this is considered an acetal. You can use these as protecting groups. If you have this one specifically right here, it'll protect aldehydes and ketones very well. And a protecting group is something that turns a reactive species into an unreactive species, and so that you can do stuff to the rest of the molecule, and then you can take it off pretty easily at the end. So in the first step, you use the first side of it to make this into a hemiacetal, and then you use the other side of it to curl up and make it an acetal, cyclic acetal. Then you can do stuff to this bromine on the other side, like turn it into a Grignard and react it with carbon dioxide to make carboxylic acid. And then you deprotect it in the last step with H+, which turns this back into the aldehyde you started with, which is pretty nifty. I added something about sugars. You'll probably see this on the ACS exam, and it's just important to be able to know what you're looking at. It's a hemiacetal most of the time. So you start with this carbon dioxide here, and this is what it looks like when glucose is in a straight chain. And if I just folded that up a little bit, it's still straight chain because I haven't reacted it yet. You can see that I can protonate, this guy is this guy. I can protonate it and then tear that off. The negative charge comes down and attacks right there because it's reactive, and I end up with this guy right here. It's an alcohol and a aldehyde, which is the same as the first step in hemiacetal formation. So when you have a sugar like this, it's going to follow a pattern. You'll see a long substituent side chain, and then over here is your hemiacetal. You can react that with another equivalent of, an alcohol in slightly acidic conditions to make an acetal. So, long chain, oxygen, that's your reactive part right there. You'll usually see it react with an alcohol, so you can just switch them out. 17 is going to be forming an imine, and that's where you react NH2 and an amine with an aldehyde. It replaces this double bond O with a double bond N, and that occurs in slightly acidic conditions. Reductive amination is an example of that. If you started with this phenyl-2-propanone and methylamine, you would end up there. That's the forming the imine. Then if you reduced it, you would get that right there. You would get both enantiomers of this. There are fancy catalysts that you can use to get one product over the other. Next, we're going to talk about the Wittig reaction. It's spelled differently than it sounds. It's German. The Wittig is German. In the first part of the Wittig reaction, you're going to make a phosphonium ylide by reacting an alkyl halide with this compound right here via SN2. And this little O with a dash through it, that's one of the benzene rings. In the second part, you're going to activate this newly formed compound by reacting it with a base to get this sort of plus on the phosphorus, minus on the carbon next to it thing going on. And bulky bases are good. And in the last step, you just sort of react it with a carbonyl group. The negative attacks the partial positive of the carbonyl, which forms a box attacking the positive of the phosphorus, and then the box collapses. And what you end up with is something that looked, see, if this is your starting carbonyl, then there's an exact copy of it right there with the double bond to the carbon that's on the terminal end of the alkane chain that you started with this alkyl bromide. So it's a way of turning double bond O into double bond C. Next, we're going to take a quick look at alpha beta unsaturated ketones. This is a ketone, that's the alpha carbon, that's the beta carbon. Since it's not full up on hydrogens, it's considered unsaturated. You have a pretty nifty resonance structure right here, which leaves a positive charge right there. And this is going to happen a lot because the negative is on a more electronegative atom. Then you can take lots of nucleophiles, like this primary amine right here, and react it, and they'll tack on, instead of attacking the carbonyl group, they'll attack the beta carbon to get things like this. Common reactions you'll see with these, just with normal nucleophiles. We'll get to the Michael addition a little later, which includes one of these. You can use cyanide, a carbon attached to SH, carbon attached to OH, a Grignard. Well, a Grignard reacts a little differently. A Grignard actually attacks the carbonyl carbon. It's the sort of exception to the rule that in H- sources like NaBH4 attack the carbonyl carbon. But if you wanted to add an alkyl group to the beta carbon, you could use something like organocuprate, CH3, CH2, 2-CuLi, and that would do what you wanted there. Next is enamine formation. You have your carbonyl carbon and a nitrogen that's attached to a hydrogen and two alkyl groups. And what happens is it replaces it with a single bond and then a double bond right next to it. It's an important pattern to remember. I'm not really going to get into the mechanism of it. Down here we need to talk a little bit about keto-enol tautomers. The basic reaction of it is pretty simple. This negative charge reaches out and grabs a hydrogen, creating an alcohol up top, but then that bond falls in to create a double bond and it kicks this up. So this is a ketone, and that's a double bond in ene, and that's an alcohol in ol. Keto-enol tautomer. You can push this to get the enol in one of two ways. You can acid catalyze it. So you catalyze the oxygen and then water can rip off the hydrogen and act as a base. Or you can base catalyze it, where you rip off the hydrogen and the negative charge pops up to the oxygen that can be ripped off by water. The really important thing about this is that enolate in the base catalyzed mechanism. We're going to use that for a lot of stuff. Reactions of enolates with Br2 as the nucleophile. This is a pretty basic reaction of enolates that you see. When that enolate collapses, it clicks off that double bond into the bromine, so you get bromination at the alpha carbon. But it's sort of unpredictable because you can rip off if you have excess base and excess Br2, you can rip off every alpha carbon. So you get lots of bromine. And once you have the three bromines there, then OH is good enough to act as a nucleophile and can kick off that stabilized carbon with the three bromines on it, and you end up with something completely different. You end up with a carboxylate and a CHBr3, which is nothing like what you would normally want out of any reaction of this sort. I just mention it because it's easy to get accidentally.